So let's go ahead and try and find a transfer function for our motor. So those previous equations give us one dynamic mathematical model of the DC motor. An alternative type of model is the transfer function. And in this case, I want to find the transfer function where the voltage applied to the armature is the input and the position of the motor is the output. You could imagine different situations where the inputs and the outputs might be different. So there could be a different situation where we want to consider the speed of the motor, and so that would be our output, or the torque of the motor, where that would be our output. So think back to how we find a transfer function. In general, we start with the differential equation model. So in this case, we have two differential equations, one for the electrical system from the previous slide was the applied armature voltage, subtract the drop across the resistor, subtract the drop across the inductor, and then we had the back EMF E sub B, and I'll go ahead and substitute in that coupling relationship where back EMF is some constant multiplying the angular speed theta dot of the rotor. And that all sums to 0. Then we also had a differential equation for the mechanical aspect of the DC motor, where we had an external torque T, which if I use our coupling relationships, the torque is equal to the motor torque constant times the current through the armature. And then we had the frictional torque opposing the motion of the rotor, and it's equal to J alpha, where angular acceleration is theta double dot. So when we find a transfer function, we begin with the differential equations. We make a decision about what's the input and what's the output. That was given. That's our input. That's our output. And think about what the second step of the process is. The next step is to take the Laplace transform of the differential equation, assuming 0 initial conditions. So if we take the electrical equation, take its Laplace transform, E sub A is just some function of time. We take its Laplace transform, we get a function of S. R sub A is a constant, so it can just come out front. The armature current, again, is a function of time, so we take its Laplace transform, we get a function of S. The inductance is a constant, comes out front. If we take the Laplace transform of a derivative, differentiation in the time domain becomes multiplication by S in the Laplace domain. And then similarly, KB is a constant, and we have the derivative of theta, so differentiation again becomes multiplication by S, and that's all equal to 0. So we'll call this equation number 1. And we do the same thing for the mechanical equation. K is a constant. The Laplace transform of I sub A is the Laplace transform version I sub A of S. The viscous friction parameter is a constant. The Laplace transform of theta dot, we get S because of the differentiation. And then on the right hand side, J is a constant, and theta double dot, since it's the second derivative, we'll have S squared, 1S for each derivative. We'll call this equation number 2. So this was the second step of the process, taking the Laplace transform, assuming 0 initial conditions. The final step is to do algebra to rearrange this all into the form output over input. Theta of S divided by EA of S. Looking at this, our input is EA of S. Our output is theta of S. And so if we look at these two equations, we have our input scattered around, we have our output, but we also have IA of S. We also have the current, which is neither our input nor our output. And so we need to eliminate this. Because it's neither our input nor our output. So if we look at this, think about how we might be able to eliminate IA of S between these two equations. In essence, we can solve one of the equations for IA of S and then substitute that expression into the other equation. So for example, from equation 2, we can solve for IA of S. So I can take this term, I can add it to the right hand side and factor out theta of S. So I had the JS squared already over there. I add the BS to the right hand side. I factor out the theta of S. And then I divide through by K. So that gives me an expression for IA of S, which I can then substitute into the other equation, equation 1. So these two terms have an IA of S. I can factor that out and sub this in. Going to the next slide, I'll complete the work. So looking at equation 1, I had EA of S. I then had the two terms with the IA of S. So I can factor IA away from the RA and away from the SLA. And then I substitute in for I sub A. I had JS squared plus BS divided by K times theta of S. Then I had the back EMF KB times S times theta of S. That's all equal to 0. So now I have a single equation only in terms of our inputs and our outputs. IA has been eliminated. And then I just want to rearrange this into output over input. So in order to do that, I'll go ahead and keep the EA of S on the left hand side, and I'll move these terms with theta of S to the right hand side. So this negative, I'll add it over, it'll become positive. This negative, I'll add it over, it'll become positive. So I'll have the quantity R sub A plus S times LA. JS squared plus BS. I'll go ahead and factor out one of those S's. So I factor out one S, the S squared becomes S. I factor out that S. I also add this term to the right hand side. That becomes positive KB times S. I factor theta of S away from the whole thing. Then one more step to rearrange it into the form output over input. The output is theta of S, the input is EA of S. So if I divide EA of S to the right hand side, I'm left with a 1 on the left hand side. And then I take this whole quantity and I divide it to the other side. quantity RA plus SLA times the quantity JS plus B. I have S divided by K, multiplying that whole thing. And I have KBS. If I take just one little simple step just to clear out these fractions, I like to have a transfer function that's just a polynomial divided by a polynomial. So if I multiply through by K on the top and K on the bottom, it's as if I'm multiplying by 1, so I'm not changing anything. And I get a transfer function K divided by S, which I can factor out. This first term has an S, and this second term also has an S, so I'll factor S all the way out of the denominator. Then I have this term due to the electrical dynamics in essence. I have this term due to the mechanical dynamics. When I multiply through by K, I'll cancel the K on that term, but then when I distribute, I'll also end up with a K on that term. And that gives us our transfer function. Again, transfer functions always have units, so let's presume that the units for position are radians and the units for the armature voltage are volts. And this gives us our transfer function, which is a dynamic model of our DC motor, our armature controlled DC motor. As I had mentioned previously, we may wish to create a transfer function for a different input or a different output. So very quickly, just by looking at this transfer function for an input of voltage and an output of position, can we think about what the transfer function would be if our output was speed? So let's call speed, or angular speed, omega. It's the derivative of angular position. So thinking about that, what might the transfer function with an output of speed look like? So taking the Laplace transform of this, we get omega of S. Here we have a first derivative, which becomes multiplication by S. And so we can see that omega is just S times theta of S. Since we have this common, we have this S in the denominator here, we can multiply through and bring it to the right-hand side or the left-hand side to get S times theta of S, which is equal to omega of S. So this transfer function will be exactly the same, except without the S in the denominator. And the units will be different. Our speed will be radians per second, and our input will still be volts.